Question 12b. A bottle of water with temperature 5 degrees Celsius is placed on a table in a room. The temperature of the room remains constant at 25 degrees Celsius. After t minutes, the temperature of the water in degrees Celsius is capital T. The temperature of the water can be modelled using the differential equation d capital T dt is equal to K multiplied by capital T minus 25 in brackets, where K is the growth constant. Part 1. After 8 minutes, the temperature of the water is 10 degrees Celsius. By solving the differential equation, find the value of T when the temperature of the water reaches 20 degrees Celsius. Give your answer to the nearest minute. This is a separable differential equation, so we can start off by multiplying both sides of the equation by the denominator dt. So we get d capital T is equal to K multiplied by capital T minus 25 in brackets dt. The next step is to divide both sides of the equation by what's inside the brackets, so dividing both sides by capital T minus 25. And we get d capital T over capital T minus 25 is equal to K dt. Next, we integrate both sides of this equation. So the integral of d capital T over capital T minus 25 is equal to the integral of K dt. And that gives us ln of capital T minus 25 is equal to kt plus the constant c. Now, raising both sides of the equation to the base e, we get capital T minus 25 is equal to e to the power of kt plus c. And adding 25 to both sides, we get capital T is equal to e to the power of kt plus c plus 25. T is equal to e to the power of c multiplied by e to the power of kt. So that's breaking up this index there and writing it as a product of two terms. Now, e to the power of c is also a constant. So we're going to let capital A equal e to the power of c. Hence, capital T is equal to capital A multiplied by e to the power of kt plus 25. Now to determine the value of the coefficient capital A. When t equals 0, capital T equals 5. So the initial temperature of the bottle is 5 degrees. So substituting these values into this equation, we get 5 is equal to A plus 25. Now e to the power of kt, where t is 0, so that's e to the power of 0, is equal to 1. So now we can solve for A. So subtracting 25 from both sides, we get A is equal to negative 20. When t is equal to 8, capital T is equal to 10. 10 is equal to negative 20 multiplied by e to the power of 8k plus 25, and this equation can then be used to solve for k. So solving for the growth constant k, firstly subtract 25 from both sides. So we have negative 15 is equal to negative 20 multiplied by e to the power of 8k. Dividing both sides by negative 20, we get 3/4 is equal to e to the power of 8k. And taking the natural logarithm of both sides, we get ln of 3/4 is equal to 8k. Finally, dividing both sides of this equation by 8, we get k is equal to 1 over 8 multiplied by ln of 3/4. Now solving for t, when capital T is equal to 20, 20 is equal to negative 20 e to the power of kt plus 25. Subtracting 25 from both sides, we get negative 5 is equal to negative 20 multiplied by e to the power of kt. Dividing both sides by negative 20, we get 1/4 is equal to e to the power of kt. Taking the natural logarithm of both sides, we get ln of 1/4 is equal to kt. Dividing both sides of the equation by k, we get 1 over k multiplied by ln of 1/4 is equal to t. And we can substitute in now the value for k. So t is equal to 1 over 8 multiplied by ln of 3/4 multiplied by ln of 1/4. And we get t is equal to 38.55 minutes. And rounding this value to the nearest whole number, we get 39 minutes. Part 2. Sketch the graph of capital T as a function of t. Note that the growth constant k is negative. Hence, for the function capital T equals ae to the power of kt plus 25, as t approaches infinity, ae to the power of kt approaches 0, hence capital T approaches 25. The graph of capital T with respect to t will look something like this. So starting off at capital T equals 5 here on the y-axis, and approaching the asymptote t equals 25 as t approaches infinity.